Hello everyone, this is the video lecture of section 5.7 and Appendix G combined. Section 5.7 is made of two different parts. First part is additional trigonometric substitution techniques in integration. Second part is partial fraction techniques in integration. Now Appendix G has a little bit further coverage of that part. So I don't think it is necessary to have a separate lecture for Appendix G. I just combined a little bit, okay, from Appendix G. So it's going to be 5.7 and Appendix G. It'll be made of two parts because it is too long. So this is first part of those combined section. All right. First of all, we want to be able to deal with sine to the nth power dx into cosine nth power dx when n is greater than or equal to 2. Now, first of all, case 1, when n is odd. So greater than or equal to 2, odd means 3, 5, 7, this stuff. So odd means that you can write it 2 times any integer plus 1. You can write it that way. In that case, the techniques involved is rewrite sine to the nth power. So 2m plus 1 power of x as sine square x to the nth power sine of x, right? Sine to the 2nth power sine of x, which is 1 minus cosine squared of x sine of x. So that when we use u equals cosine of x substitution, d will be minus sine x dx. So it's going to be simple substitution. Likewise, if you have cosine 2m plus 1 power x, to the nth power sine of x, 1 minus sine squared of x, sine of x. So let's do some examples. Example 1. Evaluate the following. Following integration a, integral of cosine to the 3rd power x dx, b, sine to the 5th power x dx. So a, okay? As we saw this, we want to write it as cosine squared x and this one more power. Leave only even power. One extra power of cosine is here. And then this, you can rewrite it like this. Cosine x dx. Now, substitution u equals cosine of x, du equals minus, cosine of x. Sine of x, cosine of x dx, right? So this is going to be 1 minus u squared cosine x dx du. 1/2 of u minus 1/3 u cubed plus c. Back to x, so 1/2 sine of x minus 1/3 sine cubed x. Okay? Why do I have 1/2? Just u. Okay. Plus c. Alright, that was easy. What about b? Again, sine to the 4th x sine of x dx. This is sine square of x square sine of x dx. Alright? Just like this, sine squared to be whatever. This is 1 minus cosine squared of x squared sine of x dx. This time we're going to use u equals cosine of x, du equals minus sine of x dx. This is minus du, minus of 1 minus u squared square du. 1 minus u squared square sine x dx is minus du. So this is minus of 1 minus 2u squared plus u squared squared, so u to the fourth. Right? So it's negative of u minus 2/3 u cubed u to the fifth plus c, or minus u plus 2/3 u to the third minus 1/5 u to the fifth plus c. So u equals cosine of x minus cosine of x plus 2/3 cosine cubed x minus 1/5 cosine to the fifth power. Okay? Now, there is a comment. First of all, remark or comment. Example 6 in section 5.6. From the recursive formula using integration by parts, we learned that cosine cubed x dx. From that result, we got 1/3 cosine square x sine of x plus 2/3 sine of x plus c. This is what we learned there. Okay? And this looks different. Well, we can show that this is actually same as the result, because this is 1/3 1 minus sine squared of x times sine of x distribute 1/3 sine of x minus 1/3 sine cubed x 2/3 sine of x plus c. 1/3 plus 2/3, so 1 times sine of x minus 1/3 sine cubed x plus c. Indeed, they are equal. Now, next comment is about remark on hint. You could say the hint. Number 1 on page 393. This is the first homework problem in this section. And you have sine cubed x times cosine square of x. It's not exactly one of these forms, but idea is same. When you have an odd power, totally odd power, 3 and 2, extra ones come out and that will be used as du, right? Of the opposite ones. So this one, odd power thing, you might want to write sine squared of x, cosine squared of x, and sine of x dx. I want to use this one as du. That means our u has to be cosine of x. Of course, du will be minus sine x dx. So this one I want to write it as 1 minus cosine squared of x. So if you use u equals cosine of x, 1 minus u squared times u squared minus du. So you can finish it. So this is the same idea as this. Odd power of sine to the n or cosine to the n. Okay? Now, next type will be, what about even power? Before we do case 2, and it's even. Before we continue, let me check recording. All right. In that case, we have to use double angle formula variant. Some people call it half angle formula. Use sine squared of x equals 1 minus cosine 2x over 2. Cosine squared of x equals 1 plus cosine 2x over 2. Some people call it power reduction formula of sine cosine. power is reduced from second power to first power. All right? Let's see. Example 2. Evaluate sine to the fourth power x dx. Okay? Solution 0 to pi. In this case, yes, before you use this, we want to write sine squared of x entire square dx. And sine squared of x, 1 minus cosine of 2x over 2 entire square dx. Okay? Now, 1 over 4, isn't it? This square over 2 squares. So I'm going to take out 1/4 out. And then numerator squared. 1 minus cosine 2x squared, which is 1 minus 2 times cosine of 2x, cosine squared of 2x. Okay? And then this one. Okay. 0 pi 1 minus 2 cosine of 2x. Now, this one is, again, we have to reduce the power one more time. 1 plus cosine of twice this power, right? X to 2x. If you have a 2x, this must be 4x, doubling 4x over 2 dx. Then what do you have? 1 over 4. 1/2 plus 1, 3 over 2, minus 2 cosine of 2x, and 1/2 of cosine of 4x dx. Okay? 1 over 4, big brace, or you can use bracket, but I don't want to use bracket here. 3 over 2, x from 0 to pi, minus, antiderivative cosine 2x is 1/2 sine of 2x. 2 is over there, so sine of 2x, 0 to pi. 1 over 4, sine of 4x, so 1 over 2, so 1 over 8, sine of 4x. Okay? This is 1 over 4. 3 over 2, pi minus 0, so pi. Cosine of 2 pi minus cosine of 0. All of them, 0 cosine. Integral multiple of pi is 0. Sine of 4 pi, sine of 0, all of them 0. So it is 3 pi over 8. Okay? Pi over 8. Now, similar strategies similar strategies can be used for, tangent to the some power of x and secant to the some power of x dx. So using 1 plus tangent square of x equals secant square of x. Use equals tangent of x, or u equals secant of x. Okay? In that case, obviously, du equals secant squared of x. In this case, du equals secant x tangent of x dx. So, I'm going to give you just example 3. Example 3 is number 7 of page 393. So I'm not going to give you the entire solution because this is homework. Okay? But I'll give you enough of hints. So let's say you have tangent cubed x and secant of x dx. And they kindly gave you the hint that you have to use u equals secant x tangent of x. Because secant x, take out one tangent, secant tangent x dx will be u equals secant x, then du will be secant tangent x dx. So you want to write it tangent square of x separated. This can be taken care of as du. So we want to write tangent squared x as secant square of x minus 1 and tangent x secant x dx. And then use this substitution. See the idea? For the hint, number 9, page 3, also 93. What is number 9? Tangent square secant to the 4th. When the combining power is even here, in that case, from 0 to pi over 4, in that case, they ask you to use u equals tangent x. Okay? U equals tangent x, well then we will need secant squared of x dx. Then we want to separate it. Square x, secant squared of x, secant squared of x dx. This will be reserved for du when you use equal to tangent. Well, we need to have a tangent then. Right? Tangent squared of x, secant squared of x equals 1 plus tangent squared of x and secant squared of x dx. Then using this, you can easily write it u squared times 1 plus u squared du, so you can finish this. So these are all similar ideas. Okay? The next one is probably the hardest. So example 4. Before we do example 4, now, if you had this, that would be the easy one, because when you use u equals a squared minus x squared, du equals minus 2x dx. So x dx is minus 1/2 of du. So it's minus 1/2 of du. This is u squared. No. Yeah. Minus 6. So this one, yeah. Minus du, this is what? Sorry about the square root of u du, right? This whole thing is u. Sorry about that. Then you can use 1/2 power, right? Adding 1 is 3 over 2. 2/3 u to the 3 over 2 plus c. So minus 1/3, 3 over 2. So having extra x was not a curse. It turns out to be a blessing. It makes us to use this simple substitution. But what about this one alone? That is much harder actually, even though it looks simpler. Okay? So that's our next example. Example 4. Evaluate integral I, which is a minus x squared is positive, obviously x must be between minus a to a. Otherwise, this wouldn't be defined, right? It's a real number. Now, the hint is, if you divide both sides by a, x over a is between -1 and 1. What other functions have this kind of range, -1 and 1? Sine theta, cosine theta, right? So, because of that, set x over a to be sine theta. Now, theta between minus pi over 2 to pi over 2, right? Now, this means that x equals a sine theta. Okay? Between minus pi over 2 to pi over 2. Then, your integral I will be written as square root of a squared minus a squared x squared. X squared will be a squared sine squared theta. And dx a cosine theta d theta. Okay? You're going to get this. Now this one, a squared factorial 1 minus sine squared theta. This one, cosine theta d theta. Okay? 1 minus sine squared theta is, this is square root of a squared, square root of 1 minus sine squared is cosine squared theta. Okay? Now, square root of a squared is absolute value of a. But a is positive, so that's going to be just same as a. Oh, I forgot a over here, a over there. And then this is square root of cosine theta, a cosine theta d theta. Now, when theta is between minus pi over 2 to pi over 2, fourth quadrant to first quadrant, that's where cosine theta is greater than or equal to 0. So absolute value of non-negative number will be just same as, so this is just same as cosine theta because of this. Alright? So you have a squared cosine squared theta d theta. Okay? And we just learned in the beginning, second part was e power. That was a squared. You use 1 plus cosine of 2 theta over 2 d theta. Half angle formula, or doubling formula variant. So this is a squared, 1 half cosine of 2 theta d theta. So a squared. Integral with respect to theta, 1 half theta plus 1 over 4 sine 2 theta plus c. Alright. It's not the end, because this is still written in theta. We have to write it in terms of x. Alright? So, because of that, we'll go further. Now, double angle formula 2 sine theta cosine theta. Alright? So 2 to cancel, 1 over 4 times this. So 1 half sine theta cosine theta. I'm going to take out 1 half out. A squared over 2. Okay? Plus c, obviously. Now, how? And then, now think about this. Theta can be easily written as x because sine theta equals x over a means that theta equals sine inverse function of x over a. Right? And also, sine theta, yeah, x over a. What about cosine theta? Now, cosine squared theta equals 1 minus sine squared theta. Therefore, cosine theta will be plus or minus. But in our range, as theta between minus pi over 2 to pi over 2, we learned that cosine theta is non-negative, right? Non-negative. So this is what? 1 minus x squared over a squared, or a squared minus x squared over a squared. Square root of a squared minus x squared. Square root of a squared is a because a is positive number. So you can get sine theta, cosine theta, theta, everything in terms of x. Therefore, our integral will be a squared over 2 theta equals sine inverse of x over a, sine theta, x over a, cosine theta over a. Now distribute. A squared over 2 sine inverse of x over a. A squared cancel. X over 2 times square root of a squared minus a squared plus arbitrary constants. Okay? So, example 5 is example 3 in your textbook. That is a reading assignment, but they didn't do this one indefinite integral first. They just did definite integral of this function. But in the end, they're trying to find this area of the circle with radius r. With radius r. And this is y equals square root of r squared minus upper semi-squared. So they want to find the area of the quarter circle. So area is a circle, area of a circle, area of circle with radius r. So a over 4, fourth quarter of a circle area will be from 0 to r of this function, right? That's precisely this. Right? Instead of a, you have r. Then you will have to just do this, right? In the end, what they are doing is sine inverse of x over r, 0 to r, and x over r, square root of r squared minus x squared, 0 to r, r squared over 2. Sine inverse of 1 minus sine of 0, sine inverse of 0, which is 0. R, if you plug in x equals r, you get r squared minus r squared is 0. If you plug in 0, also 0. Either way, both terms are 0. Sine inverse of 1 is pi over 2. So pi over 4r squared. That's quarter of a circle area. Therefore, full area is pi r squared. Okay? I just used this result. In your textbook, didn't go do this one first. Just this definition directly using this. Alright? Which is actually easier because you don't have to go back to x when you do definite integral. But I want to show you this harder one here. Okay? So I want you to go over example 3 carefully. Alright? On your own. Now, before we finish the part 1, let's do some partial fraction techniques. Just a little bit. So this is in second part is integration using partial fraction. Integration using partial fraction. Now, we are considering, let's say your function f of x is p of x over q of x, where p, q are polynomial, where such that, s dot d dot mean t dot mean such that degree p is less than degree q. Your numerator has a smaller degree than denominator. So this is any rational function. Polynomial over polynomial is a rational function. Rational function whose numerator has a smaller degree than the denominator's degree. Partial fraction applies to this type of rational function. Now, if degree of p is greater than or equal to degree q, that's not a big problem. You just have to do long division first. Then you will have quotient plus remainder over denominator. By definition, remainder will have a smaller degree than the denominator divisor. So you will end up having this form. Polynomial is easy to integrate. You just have to integrate r of x over q of x. So this is enough. So partial fraction techniques is about integration of rational function. Okay? Now, you learn partial fraction, a little bit of partial fraction in pre-calculus, math analysis. I know that some of the high schools textbook covers this, math analysis textbook covers this. But just in case you didn't learn this one, I will go over that. So don't worry, partial fraction techniques. So example 6, evaluate following. A, 1 over x squared plus x dx. B, 2 to 4, 4x minus 1 over. Both of them rational function. Your numerator has a smaller degree than the denominators. How do we do integrate this? The key step is to factor your numerator. So let's think about this. This is x times x plus 1. Then, for this one, I'm telling you this. Are you convinced this is equal to this? Think about it. Try to combine them together. Then you need common denominator. So multiply both top and bottom by x plus 1, x plus 1. X over x multiplied by x over x, so that you can make common denominator x times x plus 1. So what do you get? X times x plus 1. X plus 1 minus x, indeed, same as this. Alright? So, rewriting your original rational function as some linear combination of another rational functions where you have denominator from this factor, denominator from this factor. That form is called partial fraction. This process is called partial fraction. This one can be done easily, right? More general case here, we'll do it systematically. But anyway, because of this, this integral now is easy. This is natural log of absolute value of x. This is natural log of this one. Let's see. Some people want to write it and then on absolute value of x over using log property. Or absolute value over x plus x over x plus 1. Either way is fine. Okay? Now, the question is, what about this one? It's not that easy to split. So, So 4x minus 1 over x squared plus x minus 1. First of all, you have to factor your denominator. Plus 2 multiplied by negative, add to 1, x minus 1, x plus 2. Right? So when you have this kind of form, two linear factors like this, and numerator has a smaller degree, then you can always rewrite it like some constant over first factor, another constant over second factor. You can always write it this way. That is the partial fraction theorem. It is proven that when you have denominators factored into linear factors and your numerator has a smaller degree, then you can always write in this form some constant over first factor plus another constant over second factor. Alright? So, now how do we get a and b? Now, try to combine this one. A times x plus 2 over x minus 1, x plus 2. X minus 1, x minus 1. So you can combine this one using common denominator x minus 1, x plus 2. We want this to be equal to this. Therefore, that means 4x minus numerator has to be same as this one. Alright? Then, easiest way for doing this, first method. Well, they must be equal to each other for all x. Especially when x equals 1, definitely must be equal both sides. Why do I choose 1? Plug in 1, 4 minus 1 is 3. 8 times 3, because it makes 0. So I can solve for a. Oh, a must be 1. Alright? I plug in x equals 1 to get 0 here. What will be the next? Make this one 0. X equals negative 2. Negative 8, 1, so negative 9, 0. Negative 2, so negative 3b. B must be 3. Alright? Therefore, integral of 4x minus 1 over x squared plus x minus 2. A equals 1. 1 over x minus 1. 3 over x plus 2 dx. This integral is ln of absolute value x minus 1 plus 3 times ln of absolute value x plus 2. We don't need to combine this. Just leave it that way. So, but if you want to do 2, 4, 2, 4, 2, 4, 4, ln of 2, ln of 1, which is 0, 3, ln of 6 minus ln of 4, right? So that's going to be ln of 3, I'm sorry, 4 minus 1 is 3. So ln of 3 plus 3 times, this is ln of 6 over 4. 3 ln of 3 over 2, right? ln of 3, ln of 3 over 2 cubed. 27 over 8. Additional logarithm, multiplication. So you can write it 81 over 8 if you really want. Okay? Now, I said that this is the first method of getting this a and b. Another method here is this one. Second method is over here, we just distribute right hand side. Ax plus 2a, bx minus b. So I can write it a plus bx 2a minus b. We're saying that these two must be identical because these are true for all x. For this to be identical with this, then identical means that this must be 4, and this must be negative 1. So you have to solve this system of equation. That's easy. You just add. 3a equals 3, so a equals 1. Plug in over there. 1 plus b equals 4, so b equals 3. Just like here. Alright? So, partial fraction method. When you have a rational function where denominator has a larger degree than the numerator, then you just factor your denominator. If you get linear factors like this, then you just write it constant over the first factor, constant over the second factor. If you have another factor, then c over another factor, and so forth. But the question is, what if you have something this one is twice? Are we going to say a over x minus 1 squared, or what? So we have to consider more other cases, right? Which will be done in the second part of this combined section. Okay? Thank you.